Welcome, this is Geometry B, Unit 5, Lesson 3. We're talking about circles in Unit 5. Lesson 3 is angles inside a circle. Last time we dealt with the radius and the diameter and some segments and lines intersecting circles. Now we're going to be dealing with angles inside circles. I have here drawn circle A. The symbol for circle A is a dot with a circle, and A, circle A. Stands for circle A. Okay, and I have a central angle. It's called central angle. The central angle has the center of the circle as its vertex. This is angle CAD. Okay, and let's say the measure of angle CAD is theta. Okay. There's a couple of pieces of a circle that this divides it into. Divides the circle into two parts. One part goes around the short way. If we were to have I imagine playing duck, duck, goose, right? When you want to get from point A to point B, the shortest way to get from C to D is go straight from C to D this way. But it is conceivable to go the long way around and go all the way around this way. Okay? The yellow path is called a minor arc. The purple path or pink path is called a major arc. So the minor arc, the symbol for that is CD with a arc above it. Remember, points are always capital letters. The major arc requires 3 letters, because anytime we use 2 letters, we're implying a minor arc, we're implying the shortest distance between the 2 points. The major arc is going to be CED. So 3 to indicate we're going around the long way. Okay? And of course, we measure, M stands for measure, the measure of arc CD is the measure of the central angle, theta. Okay? Whereas the measure of arc CED is going to be 360 less theta, because it's 360 degrees all the way around the circle. So 360 less theta. 360 less theta. Okay, so that's some vocabulary. Major arc, minor arc, central angle. The sides of the central angle, the legs of the central angle are radii, or each is a radius of the angle. Okay, so let's go now to our second case. This case is a case called an inscribed angle. Inscribed angle. Notice the inscribed angle has its vertex not as the center A, but as a point on the circle. So it connects 2 other points on the circle. So the vertex is on the circle. So the angle CDB is a central angle. And let's go ahead and draw, or the inscribed angle is an inscribed angle. Let's go ahead and draw the central angle CAB. And let's go ahead and draw that. CA. And CB. Okay. You recall from the last slide, if we measure the arc CB, the measure of arc CB is given by the measurement of this angle right here that we call theta. Okay? The inscribed angle theorem says this, and I'm not going to prove it. The lesson goes into a little bit of an explanation, but not a rigorous proof. But the inscribed angle theorem is one of the big ideas of this unit. And it says an inscribed angle is 1/2 the intercepted arc. And in short, what this says here is both angle D and B intercept the arc CB. They both intersect the arc CB. Let me highlight that. Okay. The intercepted arc is CB. So the measure of arc CB, and we can put the measure on theta, on the angle, or we can put it up here on the arc. That they both intercept the same arc, therefore by the inscribed angle theorem, angle D is 1/2 theta. To give you an example, a specific example, let's say theta was 90 degrees, then half theta would be 45 degrees. Okay? Let's say that half theta is 30 degrees. Whoops. One more time. 30 degrees, then theta must be 60 degrees. Okay? Whatever the inscribed angle is, the central angle or the intercepted arc is twice that, or whatever the intercepted arc is, the inscribed angle is half that. Right? They have a ratio of 1 to 2. So let me leave it 90 degrees, 45 degrees, because that's kind of what it looks like here. Okay, that's the inscribed angle theorem. You're going to use that lots. Okay. Now I have a pair here of inscribed angles, if you can kind of see them. Angle E is an inscribed angle and angle D is an inscribed angle, and they both intercept arc BC. They intercept arc BC. Let me highlight it here. So let's say arc BC has measure theta. Now I'm not going to draw the angle BAC because that would greatly complicate the drawing. But the intercepted arc has a measure of theta. We say the measure of arc BC is equal to theta. That means angle E, which intercepts the same arc, must be 1/2 theta. That means angle D must also, because it intercepts the same arc, be 1/2 theta. And we call this a corollary to the inscribed angle theorem. Inscribed angles, inscribed angles, intercepting the same arc are equal or congruent. Okay? Since angle E, the measure of angle E, equals 1/2 theta, and the measure of angle D equals 1/2 theta, they must be equal to each other. The measure of angle E equals the measure of angle D, and here's how you're going to be given this in a question, or at least one of the ways. You'll be given maybe angle D. The measure of angle D is 20 degrees. What is the measure of angle E? In that case, X is 20 degrees. So recognize that two inscribed angles that intercept the same arc are congruent to each other. Or vice versa, angle theta, or the measure of this arc, must be 40 degrees because the central angle or the intercepted arc is double the inscribed angle. Got to be careful of my words, make sure I use the right words. All right, so that's case number 3. They've got a lot of cases in this unit. Okay, case number 4, this is what's known as a circumscribed angle. Remember, circumscribed means to draw around. A circumscribed angle. A circumscribed angle is made up of tangents, two tangent segments. Let me label this B and C and D. So angle BCD is a circumscribed angle. Okay, let's label it X. Okay, let's say I happen to know this angle right here. We'll call this arc BD theta. Okay, arc BD is theta degrees. That means angle A or BAD is theta degrees, right? And so we also know, if you recall, that tangent segments are always perpendicular to the radius. Okay? And also, we happen to know that a quadrilateral, all four angles of the quadrilateral add to 360 degrees. So we can say that theta plus x, oh, no, plus x plus 90 plus 90. You're thinking, where am I going with that? 90 plus 90, so theta and 90 and 90, and x must equal 360 degrees. Now 90 and 90 is 180. If I subtract 180 from both sides, I end up with theta plus x equals 180. Or if I were to solve for x, x is 180 minus theta. Let me show you how you're going to use that. Basically what it says here is that these two angles, the intercepted arc and the circumscribed angle, must add to 180. Okay? So if we're told that the intercepted arc is 150 degrees, then x must be 180 minus 150, or 30 degrees. Okay? Vice versa, if I was told that x is 25 degrees, then theta would make up the difference for 180, right? Let's do this in a different color here. Let's say that x was 25 degrees, then theta would be 180 minus 25, or 155 degrees. Okay? They must always add to 180, the intercepted arc and the circumscribed angle. Okay, so I think I've got one more case here. This final case here is not nearly as complicated as some of the last one we did here. But here it is. We have what's called a diameter. Let's label this B, B, and C. And the measure of arc BC, if I were to measure the arc, measure of arc BC is 180 degrees because it's half of a circle. Okay? Well, if I look at B, that's good. Let's see, BEC, angle BEC. BEC is an inscribed angle that intercepts a 180 degree angle. Therefore, it must be 180 divided by 2, which is what? 90 degrees. Okay? So this is another corollary of the inscribed angle, and that is this. An angle inscribed in a semicircle is 90 degrees. An angle inscribed in a semicircle is 90 degrees. If I were to sketch a semicircle, right, where the edge is a diameter, and inscribed an angle that touches the ends of the diameter, the angle is 90 degrees. Okay. All right, and that's nearly 15 minutes, so I went a little long on this, but we had a lot of cases.